So in section 3.5, we have a question on voltage regulation. The question is, consider the voltage regulator circuit shown in this figure, and the value of R is selected to obtain an output voltage V0 across the diode. So V0 is across the diode of 0.7 volt. So this is 0 volt, this is 0.7 volt. And we have to use the diode small signal model to show that the change in output voltage corresponding to the input corresponding to a change of 1 volt is V plus, corresponding to the change of 1 volt in V plus is del V naught over del V plus is equal to V thermal voltage over V plus V thermal voltage minus 0.7 volt. And this quantity is known as the line regulation and usually expressed in millivolt per volt. So first we have to understand what is voltage regulation. So voltage regulation refers to the ability of the circuit to maintain a stable output voltage. Stable output voltage V0 across the load, and in this case across the diode, and despite the variation in the input voltage. Voltage regulator adjusts the current flowing through the components like the resistor and the diode to ensure the output voltage V0 stays close to the desired value. In power supply circuits, sensitive electronic components like the microcontroller sensors need a constant voltage to operate correctly. So in this problem, we have to analyze the voltage regulation using a small signal model for diode. We know that diode small signal model approximate the diode's behavior for a small variation in voltage. The current through the diode, which is ID, will be equal to IS, which is the reverse saturation current. Reverse saturation current multiplied by e to the power Vd over Vt. Vd is the voltage across the diode and Vt is the thermal voltage, which is typically around 26 millivolt at room temperature, minus 1. So this is the equation for diode small signal model. And for a small change in P plus, the relationship between the change in the output voltage del V0 and the change in the input voltage, which is del V plus. This is the change in input voltage, and del V0 is the change in output voltage. So it can be derived by linearizing the diode's current voltage curve using small signal resistance, which is RD. So RD is the diode's small signal resistance, and we know RD is equal to VT over ID. So from here we can derive the regulation equation. The total voltage drop across R and the diode V plus minus V naught. So if we look at the diagram that we have, we can see that V plus will be ID multiplied by R. ID is the current flowing through the resistor, and then a resistor multiplied by ID, and we have to add V0 to get the total voltage, which is V plus. And then we have to do small signal analysis. So small signal analysis. For small changes in input voltage del V plus, we analyze how V naught changes by differentiating both sides of this equation, which is V plus is equal to IDR plus V naught. So if we differentiate it, we take the derivative, which is del V plus is equal to R del ID plus del V naught. We can also do something with the figure that we have. We can draw it in this way. So this is our input voltage del V plus, and then we have the resistor R, and then we have RD, which is the diode resistor, because we are using small signal model of the diode, and then this part is the output voltage that we have, and then we connect this to the ground. So this is the small signal model. And now if we want to find the ratio of V del V naught over like the ratio of the output voltage and the input voltage, we just need to do some calculation, which is we just take as we know that RD is equal to, so we know RD is equal to VT over ID. From this equation we can get the value of ID. So del ID will be equal to del V naught over RD. So we can take this equation and we can substitute this here. And if we substitute that here, we will get del V plus is equal to R multiplied by del V naught over RD plus del V naught. Now we need to also think about solving for del V naught and del V plus, because what we're trying to find is the ratio of the output voltage and the ratio of the output voltage and the input voltage in terms of the input voltage and the thermal voltage and the diode voltage. So for this thing we have to just use the you have to just like solve for del V naught and del V plus by rearranging the terms in this formula. So we can, if we rearrange it, we get del V naught over del V plus is equal to 1 over 1 plus R over RD. Now we can, again we know RD is equal to VT over ID. So ID is approximately, we know that it will approximately be sub V plus minus 0.7 over R, because ID is, if you look here, ID is V plus, this V plus minus 0.7 over R to get ID. So the V plus here minus this voltage 0.7 over R gives us ID. So from here we can replace the ID with this part, and then we can substitute RD is equal to VT. We can substitute this part with this thing and then this part with this thing, and if we do that we will get our final equation as del V naught over del V plus is equal to the V thermal voltage over V plus V thermal voltage minus 0.7. So this shows us the output voltage change relative to a change in the input voltage depending on the thermal voltage V thermal and the input voltage V plus and the diode threshold voltage of 0.7 volt. So this is our final formula.